Okay, so good morning, everyone. I hope you had a good weekend. So we're going to look at the proof today. Are there any questions from last time? All good? Okay, good. Yeah, so today will be fun because finally we won't be hand waving. We'll actually write the proof. I mean, we'll see how far we'll go, but at least that's the plan.
So this is proof for certified deletion.
Yes. So I'll give you the construction. I suppose I don't know if he'll all. I think no. I'll have to write the construction explicitly once. But the idea is what we already described, right? That you have these two parts. Okay, so yeah, so it's going to look a little bit dry, but then everything will fall. Everything will come together towards the end. So let's start. So we're going to look at the XOR extractor. Okay. So what we want to say is that the XOR function is a good randomness extractor even in the presence of side information. So it'll become clear what we mean in just a second. Sorry, from quantum sources. Even in the presence of side information. Okay. So here's the statement. So we let X be an n-qubit register. We consider gamma AX to be of the form.
Okay, right from side so that you
Yeah, sorry. Yeah, this is a bit harder, which. Sorry, yeah. So summation u such that HU is at most n by 2. So H, this is notation I'd introduced last time. So let me just quickly remind you because it's been a few days. So H of X, so X is a string, okay? So this is just the Hamming weight, so number of non-zero entries in X, okay? This is a binary string. Omega X is, let's say, n-bit binary string. This is H, okay? My H and N start to look similar, but okay. And omega X or WX, which is like the relative weight, the relative Hamming weight, or relative Hamming distance. So this one is, here, let me write it. So this is Hamming distance, and this is relative Hamming distance. Okay. Okay, so H of U, it's basically saying you'll sum over all strings with Hamming weight at most n by 2. And oh shoot, wrong page. Okay, And so on register A, so note I didn't make any comment on how big A is, so A can be arbitrary. So you have some state A, some state psi sub u on A tensor with u on X. Okay. So you assume this, and then you let rho A P be the mixed state. Maybe I shouldn't write cursive. Obtained by measuring X in the Hadamard basis. To produce a string X, right? So you measured it in the Hadamard, you got some string X, length n, and writing the XOR of X, so you XOR every bit into a single bit in register P. Okay. So you start with this state, yeah? You measure this in the standard basis, you XOR it to compute a single bit, and you put that into P. Okay. So that's the mixed state that you get. That's what it's saying. Is that okay?
Where is the measurement here?
X, yeah. So you measure the register X in the Hadamard basis, you'll get some answer, you XOR it into a single bit, and then this is the state set. So you're just writing the state as rho AP. Okay. So if you do this, then the claim is, then it holds that rho AP is the same as you trace out register X, in gamma, and you have 0 0 plus half 1 1. Okay. So intuitively what is happening is the statement clear? Yeah? Okay. So intuitively what is happening here, we are saying that, you know, after you applied this procedure, it's an XOR, right? So that's why it's called this XOR function, right? So what you're doing here is you're measuring this register U in the Hadamard basis, and you're XORing it. And then the claim is that even if the, you know, suppose A is the adversary, right? So even if the adversary had some correlation with you to begin with, if you started with that state, if you could somehow guarantee that this was the initial state, the entanglement of the adversary with you, and you measured U being X, right? And you measured X in the Hadamard and you XORed, then you're guaranteed that your register is uniformly random, independent of what the adversary held, okay, in general. So that's kind of the main statement that we'll need later. So that's why we're interested in this. Okay, is the intuition and the motivation clear? Okay. So this is just yeah. So this is gamma was on AX, right? So okay. So let's now look at the proof. Okay, So here's the story. So we're going to use write the state. So we write the state on AXP from applying Hadamard to X and recording XOR in, recording the XOR in P. Okay, so that's what we'll do. We'll just write it out explicitly. So here's the definition. So psi AXP. Okay, so first definition, Px is just the parity of X. Okay, so this is Xi. Okay, and then we define this psi to be the following object: 1 by 2 to the n by 2, sum over sum over x in 0, 1, n, u such that each of u is at most n by 2 minus 1 u dot x psi a x and this is what we are calling okay, so this is just I should keep this on. So all that we've done is we basically measured this register X in the Hadamard basis. Okay.
Measure, you applied the h1 u1 h1 power u1 tensor h2 power u transform.
Yeah. So yeah, we're doing it coherently, but the idea is that you get the outcome X if you were to measure. So I'm just writing it coherently, but the result is stored in X, and then you're computing P of X. Okay. So that's the state that you get if you were to do this. Okay, which is exactly what the procedure is asking us to do, except that we have kept the X register around. Okay. Now we note that trace X of psi equals rho A P, right? So that's just by the definition of psi and the definition of what we wanted rho X to do, correct? So if you throw away the X register, it's essentially equivalent. Okay, good. And then this also means that we can compute rho AP. So when we compute rho AP, what we'll get is 1 by 2 to the n sum over, maybe I should write from the other side now. Yeah, writing tilted is a little bit harder than.
So could you explain first line a little bit more?
Just a sec. Let me finish this, and I'll come to it. Yeah.
So I want to understand. You had psi a, so you have gamma ax.
Gamma AX.
Yeah. So on gamma ax, I apply say Hadamard on each qubit with some string u. Is that what you're doing?
Yeah.
And then how do I store px? And
You
what is
can.
the operation behind it?
Yeah, maybe the easiest way to think about it is that you measure in the Hadamard basis. Yeah, so Px first of all is simple, right? Because once you've computed X, from this you can directly compute P of X. So there's not.
What is this operation?
It's just this, right? Like you can. If you're going from x0, you can always do this, right? X to whatever function f of x you like. This is always. So that's all I'm doing.
So you call some parity function there.
Yeah. Is that okay?
And usually here this f is oracle, but for parity you know actually the operation.
Yeah. This is, you can write any you can convert any classical function into a, like a if you have a classical circuit for f, you can make it into a quantum circuit
No, that is
by
true. I'm asking
making it reverse.
Usually it's oracle.
Yeah.
But
It can
for
be
parity
whatever.
it's easy, right?
Yeah. The key concern should be that it should be efficient, right? That's what we care about. And as long as f is efficient classically, it will also be efficient quantumly, because you just do the same thing reversible, but with reversible gates, essentially.
Yeah.
Okay. Okay, so we have this.
Like just a small thing. How do we get an extra 1 by 2 power n by 2 in row? First part is 2 power n by 2. Second part is 2 power n.
Did I mess up? Oh, because it's a density matrix, no? So, what do you mean?
First one is I think I'll probably explicitly compute it later.
No. I mean, this is like, you know, if psi is this, right? So if psi is 1 by root 2, like 0 plus 1, right?
Oh, okay. Yeah.
So if you write psi, you'll get half, and then, you know, ij, whatever.
Okay, yeah.
Yeah, there's nothing deep here. This is calculation. Okay.
The first line over there says write the state on A tensor T.
AXP. There's register X, right?
Right. Wait, what is AXP again? Sorry. Like AX is the complete system, right? Initially.
Yeah. So I'm defining a new state,
okay.
right?
Okay.
And I'm saying that if you were to trace out X from this new state, it would be the same as that operation. Yeah. It's not doing anything very deep. It just makes it easier to argue, I guess. Okay. Okay, so now there's going to be some algebra. So let's do it. Okay, so now we have 1 by 2 to the n. You take x such that p of x is 0. Phi x, phi x. Sorry about that. So tensor 0, 0 plus 1 by 2 to the n, sum over x such that p of x is 1. Okay, phi x, tensor 1, 1. Okay, I've done nothing, I've just expanded it. Okay.
It looks everything is low depth still, because this P parity can be computed in low depth. So there is no polynomial depth as such here.
Right, I haven't thought about the depth, but you might be right. Right. Okay, and then 1 by 2 to the n, sum over x. Yeah, so that line equals the following, right? So phi x was that object, so we'll write out the object explicitly now. So the object was u1, u2, such that hu1 and hu2 both are at most n by 2 minus 1 u1 x over u2 dot x psi u1 psi u2 tends to 0 0. Okay, and plus 1 by 2 to the n, the same thing except now x is restricted to px equals 1. So u1 u2 such that hu1 hu2 at most n by 2, and you're going minus 1 u1 XOR u2 dot x psi u1 psi u2 tensor 1 1. Okay, haven't done anything. I've just written out the expression for phi sub x. Okay, good. And now what we'll do is we'll swap the sum. So we'll get these summation over u's out. So this one can write as u1 u2 such that hu1 and hu2 are at most n by 2. Then psi u1 psi u2 tensored with 1 by 2 to the n, summation x such that p of x is 0 minus 1 to the u1 XOR u2 dot x 0 0 plus 1 by 2 to the n sum over x px equals 1 minus 1 to the u1 XOR u2 dot x 1 1.
So can you explain that, like how are you getting it u1 XOR u2 dot x from the
Yeah, you just multiply it, right?
yeah.
So what do you get if you do
XOR like u dot x.
u1 dot x minus 1 u2 dot x? Yeah. So you can write it as it's binary, right? Like so you can just you can write it as u1 dot x plus u2 dot x, right? But it's just going to be binary, so it's just modulo 2, so you can put a XOR, it doesn't matter. And then it's just the distributive property, whatever. Okay. Okay, so this is fine, right? I mean, I've not done anything really so far. Yeah? Okay, good. So now comes the claim. Okay. Okay. Okay, so what is the claim? So now the claim is, so this claim is a part of the proof, okay? So this is how they, if you're not very familiar with how they write proofs, they'll put claims within the proof, and then we prove the claim. So this is the following statement. So for any u 0 1 n such that u is not the all 0 or the all 1 string, okay, it holds that sum over x for px equals 0 minus 1 to the u dot x is going to be the same as sum over x px equals 1 minus 1 u dot x is going to be 0. Okay, so the claim is that the only u's that are going to contribute here are the cases where they're not all zeros and they're not all ones. where for all others, the only ones that can contribute are the ones for which it's all zeros or all ones. All the others will add up to 0. Okay. So yeah, so let's assume this claim is true for now, and we'll do the proof of the claim in just a bit. So okay, so assume this is true, okay? So proof deferred. Okay, so using this claim, what do we get? Okay, so first of all, we note that U1 XOR U2 is never 1 to the n, okay, in this setting. So in the sum, yeah. So in the sum, U1 XOR U2 is never 1 to the n. Do you see it?
Also 0 to the n.
Yeah. But 1 to the n you see, right?
Yes. How long that claim?
Huh?
If I believe the claim.
Yeah, of course. Believing the claim, yeah. Assume the claim is true. Then this is, yeah, is it okay? Okay. Okay, but it is possible that U1 XOR U2 is 0, right? Because they just have to be the same, right? It's an XOR, so it's not a problem. So this will happen whenever U1 equals U2, right? And in fact, it's equivalent, correct? Okay, and so one can think of sum over x, say px equal to 0, minus 1.
Why did we need the
Sorry.
claim for saying U1 XOR U2 is not 1 to the n?
Sorry, why did we need a claim?
Yeah, why did we need the claim for U1 XOR U2 is never 1 to the n?
No, these are just observations. I'll use the claim later. Yeah. But, I mean, I'm singling it out because these are the only two terms that we have to worry about contributions coming from. I'm saying one of them doesn't actually appear in the sum, so we don't have to worry about it. This one does. And so what does that mean?
No, but without claim, how will I know that this can never happen?
Because we
Oh, what did you think? Sorry. Oh, that's why you were asking what was the, yeah.
Oh, because they
The way it's yeah, the claim doesn't say anything about U1, U2, right? That U1, U2 are just appearing in the sum. Yeah. Sorry, I think I misunderstood what you were saying. I thought you were.
yes.
Yeah. No. You're right. It doesn't. Yeah, this statement doesn't follow from the claim. Yeah. Thank you for spotting it.
And why this can be 0 and
Oh, why can what be 0? This? Oh, you're just summing them, right? So there's no. For example, when U1 equals U2, right? You could have a string with Hamming weight. Say, if you could just have this string, right? Like 1 0 0 0. It could be that U1 and U2 are both 1 0 0 0. So it's possible that U1 XOR U2 becomes 0.
these are separate observations.
Yeah. This is NB. Now these are different nodes. Yeah. Okay. Is that okay? Okay. And so now what we are saying is that one can write what did I do? Okay, so I'll write something and then we'll see if I wrote it right. Because I think Okay, yeah. So let's see if I messed up. Okay.
And also second statement, it is possibility, right? It's not always true. So the way you are writing, the first sentence is like u1 plus u2 is never 1 to the n.
Yeah.
The second sentence is not like u1 plus u2 is always 0.
Yeah. It's just this equivalence, right? It just says whenever there's 0, they're equal, and the fact that this can happen, yeah. So this can happen for some choices. Okay, so now what is the statement? The statement is that for x such that, so you do the sum, okay, u1 x or u2 dot x. So this essentially behaves like a delta function. So it's basically like, up to normalization. So what this is saying is that if u1 and u2 are not 0, if the XOR is not 0, okay, then this sum will disappear, because you're summing over x's, and whether you sum over odd x's or even x's, it should disappear. Is that even correct? Am I doing something wrong?
Yeah, I think it's okay.
If it's 1, it should disappear.
What is
If the XOR.
Yeah, if it's anything other than 0 is basically what I'm checking. Yeah. When it is 0, it will evaluate to some constant, like whatever 2 to the n, however many things you have. And if the parity of x is 0, so if you take a single bit, then nothing contributes, does it? No. If you have a single bit, then x can be only 0, right? It cannot be 1.
But if we have a single bit, then u is either all zeros or all ones.
Right. So if u is all zeros,
So that
then
means not what we are doing in the claim, right?
so if u is 0, then it would be okay, you're right. And if u is 1, then it wouldn't, that situation doesn't arise. And if you have say u1 plus, so suppose u1 equals u2, no, it's not equal. So let's say the XOR happens to be 1 0, right? And then the choices of x can be yeah, so the parity has to be 0, so you could have a contribution from okay, so one of them will fix the parity, I guess. Yeah, so you can have 1 1 or 0 0, and then it should add. Yeah, so this seems to be correct. Okay. Okay, so this thing, huh?
You will not prove that?
I mean, it's elementary. I just got confused. You can. This is just a delta function, right? Because what is the intuition is just that if this is non-zero, right, then pluses and minuses will come in equal portions and they'll cancel.
So this is just the application of the claim, right?
Is it the claim?
Yeah.
Okay, yeah. So you use the claim. Good. Yeah, which we'll prove actually. So it's non-trivial. Sorry. So I misspoke. So yeah. So you can use the from the claim. Okay, good. Yeah. So from the claim we know that.
No, but how did you get rid of 1 to the n?
We're not in the 1 to the n case, right? We just said that u1 XOR, that never happens.
Yeah, then it follows from the claim.
Okay. So this basically behaves like a delta function, u1, u2. Because it's only when they match that you get a non-trivial contribution. And when they match, you will basically have 2 to the n or whatever, however many parity bits you have. So it will be 2 to the n by 2. Or 2 to the n minus 1, probably. right? Because this half the bits would be odd, half would be even. Okay. So that's the observation.
This is true for px equal to 1 as well, right? From the claim.
Is true for px equals 1 as well, yeah. Also for px equals 1. And yeah, so exactly. And also for basically the same thing, right? That will also behave as a delta function. Okay, good. Yeah, I'm sorry, I did this like 2 weeks ago, so I'm a little bit rusty on how the reasoning went. Okay, and then apparently what one can write is the following. So one can write u such that hu is at most n by 2, psi u, tensor half 0 0 plus half 1 1, right? Because yeah, so these guys become, each one of them becomes a delta function, right? Between u1, u2, u1, u2 from that observation. And so then you can solve the two sums, you can drop one of them in each case, right? So, and then you can relabel you whichever one you want. And this is what? Well, then this is exactly the same as tracing out register x on gamma gamma, right? Tensored with what we wanted, 0 0 plus half 1 1. Okay. Yeah, maybe I leave the proof of the claim as a homework exercise. I'll tell you where the reference is and you can read it. I think that may be better because otherwise we'll not be able to make much progress with the remaining thing. Or I can put a video, whatever. It's not very complicated. Okay. All right. So at least, yeah, as far as this is concerned, assuming that the claim is true, the proof is done, right? The whole thing. Okay. Now, this was part of the prerequisites. Apparently, there's quantum rewinding that's also needed, but I couldn't tell where it was used, so I'm not going to explain it to you. Maybe it's used in some later proof that I didn't use, or that I didn't get to. Okay, so now we can actually start the main theorem.
So could you explain the name, the XOR extractor? So this is done, right?
Yeah.
So what does it mean, and what does it mean randomness extractor?
Yeah, so okay, so what do we want? We want to say that, yeah, let me, so what we were saying was that if you had this state, right, it was, what was the, yeah, there was something, right, like, yeah, let me write down the state. Give me a second quickly. Yeah, so it was psi sub u, right? Yeah, good. Yeah, so the state was this, right? So gamma was of this form, right? Psi u tensor u ax sum over u such that hu is at most n by 2. Okay, so the point was that suppose you have by using some kind of reasoning, you're able to argue that this is the state that the adversary and you hold. Okay, so you're holding x and the adversary is holding some side information about you. So if you're able to get to this form, what you normally want to do is you need to hide a bit. Okay, and the way we normally hide a bit is by XORing with a random bit, right? So what they're trying to do is they're saying if you come to this step and you make a certain measurement, then you're able to produce a uniformly random bit, which is uncorrelated to what the adversary was holding. So you're extracting randomness from the state in this precise sense. Okay, how it is used we'll see, but as far as the statement is concerned, it's just saying that even though the adversary is holding some side information, you're able to argue that once you've done the Hadamard measurement and XORed it, right? Because even after doing the Hadamard, it is correlated. So it's crucial that you XOR it, right? That's how we were able to get rid of all these correlations. So that's what the key thing is, that even after doing the Hadamard, if you XOR it, you actually end up getting a state which is completely uncorrelated with the adversary. So that you're extracting randomness from the state in this sense. Because what is randomness, right? We basically want the randomness to be private. That's the whole point. That's, yeah.
Also, is it like you were able to get randomness without really measuring? Because all you did was apply unitary operations. Now the last bit is
No, there was
we traced out, right? Like we purified it and then we traced out, which is essentially the same, but you know.
okay.
Yeah, you do have to trace out, otherwise you will have correlations.
Without measurement, you will not know what to XOR, right?
You can do it coherently. That's okay. Like if you have superposition over x, like the same operation, it's bilinearity, right? If you have x0.
Yeah, but you didn't extract anything, right? You can write it in the quantum resistant coherent form.
Yeah,
But you will not extract anything without measurement.
yeah. You have to. Yeah, I mean the point is that if you're keeping track of what the output of the Hadamard measurement was, then you will have correlation. So you do have to throw it away if you want uncorrelated. Okay.
So the way you are arguing, as long as I have a product state at the end, will I call it good? Because you have maximally mixed state in this case. So suppose instead of maximally mixed state, I have something else. Doesn't have correlation, but you will not call it randomness extraction.
Yeah, the strict meaning I think we'll come to. We'll also do certified randomness, I guess, at some point, and then we look at it much more carefully. Here, the whole point was that you want to start with, like, you want to argue that your initial state is this, which is useful because that's what they end up getting, that the adversary holds some information, and nonetheless you're able to extract uniform randomness out of it. So when they produce the deletion certificate, you can argue that once they've produced it, they're XORing with bits coming like which are uniform, and so therefore they don't have the information, something like this. We'll see. Okay, shall we continue? Okay. Oh, wrong page. Okay, so the theorem is the following. This is going to take a little more space than I have here. Okay, so let's write down the statement. So the theorem statement is the following. So you have the following things. So you let. So this is a bit more abstract, okay, than the thing we discussed in the informal proof, but it's going to be okay. So these are quantum operations. So this is, okay, I'm just calling this, let this be a quantum operation. So remember, we want to talk about some notion of efficiency, right? So here it's saying that you have some operation for every value of lambda. So instead of taking it uniform, they're taking it non-uniform. Okay, you remember uniform, non-uniform, right, from your complexity theory and so on? No? Okay. Yeah, so this is just saying that for every value of the security parameter, you're allowed to construct an individual algorithm. Okay? And the claim would be as lambda increases, we have security. Okay, so with three, so it takes 3 arguments. If you don't want to think about it too much, you can just think that you give lambda to a Turing machine, okay, and the Turing machine outputs a description of a circuit, a quantum circuit. Okay, and what does the quantum circuit take as arguments? It takes the following 3 as arguments. So take the proof is for non-uniform, but you can, for simplicity, take it to be uniform if you want. Yeah, what I just said is uniform. Yeah, exactly. Yeah, sorry. Yeah, I'm a bit slow, man. It's okay. Okay, so lambda bit strings. Oh, sorry, it takes a lambda bit string theta. It takes 1 bit p prime, so a bit. Okay, and it takes a lambda qubit register. Okay, so take, damn it, second time. Need to find a more permanent solution. Okay. Yeah, sorry about the noise. Okay, so these are the arguments. Okay. And then it takes a lambda in n. Okay, so these are the two things. So you let a lambda be a class of adversaries. Oh shoot, no cursive. Adversaries such that for all theta in 0 1 lambda, all b prime in 0 1, and psi in A tensor C, okay, where C is arbitrary. Yeah, so the Hilbert space corresponding to A is curly A. Oh, okay. The following holds. So such that for all of these quantifiers, you have that you give to A lambda the output of Z lambda. What does Z lambda get? Z lambda gets Z B prime A, okay, and it's holding C, and it outputs 1 against the following, in which A lambda is given the output of Z lambda, except that now instead of theta it's given 0 to the lambda, okay, and it's given register A, okay, and register C, okay. So we want this probability to be negligible in lambda. Okay, or in other words, I'll explain this in a minute, but basically all we are saying is Z lambda is semantically secure against A lambda with respect to the first input. Okay, so far we are still in the hypothesis stage, okay. So we said that, so Z lambda is some class of operations, okay, that we described. And now what we are saying is that you've constructed the Z lambda in such a way that whether you give the Z lambda theta or 0 to the lambda, basically the first input, whether you give it theta or 0 to the lambda, no adversary can distinguish the two cases, even if they had some side information in register C. Okay.
Do we assume anything about the adversaries?
Yeah. So we're assuming that it's from some class, so you can take it to be QPT and so on. So it's a very general statement. You can apply it. Yeah, that's the whole point. Like they're doing it abstractly so that they can apply it to different situations. For our purposes, it would just be QPT because we look at encryption schemes and so on. Okay. Okay. So you have these two properties.
So this is notion of security in general.
This is notion of indistinguishability. So semantic security and indistinguishability is like the simplest notion of encryption, right? That we had.
Why is that semantically secure?
Well, semantic. So in the wait, I don't remember. Were you there for the crypto review?
No, but semantic I know.
No, I think you were there.
First class I
No,
got.
I think it was done as a separate lecture uploaded on YouTube.
Oh, okay.
The semantic security is equivalent to the normal definition of security.
Okay. In any case, the point is that we have this indistinguishability definition, right? Whether I give you an encryption of C given an encrypted, whether I give you M0 or if I give you say C0 or C1, right? Encryption of M1, that no adversary should be able to distinguish these two, right? So this is essentially the same as semantic security. Like the proof is non-trivial, but you can show that it's equivalent to semantic. In the information theoretic setting, it's easier to see, right? Because there you show that the distribution of C given the message was M0, so this probability is the same as the probability that you got some ciphertext given M was M1. So this is the notion of ciphertext indistinguishability, but you can also show that this is the same as probability M is M given whether or not you know the ciphertext. So this is the more semantic security thing, right? Like your distribution over the messages, like your knowledge about the messages is unaffected by whether or not you see the ciphertext. So this is semantic security, this is indistinguishability.
So they are equivalent.
Yeah, they are equivalent in the information theoretic setting. That's relatively easy to see, but in the computational setting, I think it's more involved, and so people just use the indistinguishability definition because it's easier to work with. But they use the word semantic because to distinguish it from CPA and CC and so on.
Yeah, it has nothing to do with like complexity causes the semantic. It's different.
Oh no. Yeah. That syntactic semantic. Yeah. That's a different thing altogether. You're right. Well, actually, there may be some relation, but I have studied them in different contexts, and I just meant it in the sense that I described it. There may be some connection actually. Yeah. I don't know. Okay.
Here this Z lambda is this like the encryption?
Yeah. Let me write the statement of the theorem. These are still the hypothesis part. Yeah. Once I write the statement, hopefully it would become a bit more clear. Okay, so that was the second part. The third part. So this is still the hypothesis, right? The let part. Okay, so now you take for any right, non-coercive. So for any a lambda is a natural number. Consider the following. Distribution. What is the distribution? This is the distribution. So you have z tilde lambda, a lambda b, lambda n, produced by the following. So what's the process? This is the usual the security definition that we looked at like 10 times. Okay, so what was the notion? The notion is a bit more general now. So you have x comma theta, and I guess it will answer your question as well as you'll see. Okay. So what you do is you send the following. So you send z lambda of theta be XORed with XOR I such that theta I is 0 of xi and x sub theta. Okay, where recall x sub theta was just, this is recall, was just h to the theta acting on x. Okay, so you send it. So basically, so z lambda was taking 3 inputs, right? So now the first input is theta, okay, and we know that the first input is that z lambda cannot distinguish. Like there's no algorithm that can use z lambda to distinguish theta and 0 lambda. Okay, and then these are the other inputs that you're using z lambda. So basically, you can think of it as whichever form of encryption you like. And then, so you whatever the output is of z lambda, you send it to a lambda, and then you have x prime and a prime, which are returned as outputs. And if xi equals xi prime for all I such that theta is 1, output a prime, else output perp. Okay, and that's the adversary. So this z tilde lambda is the output of this process. So you use z lambda in this way, and whatever output you get, you output that. So this is the output of z tilde lambda, okay, and it's subject to b because you're using b here. So you put b here. Okay, so is this clear? Yeah.
So to say z lambda is semantically secure with respect to the first input.
Yeah, that's
Wouldn't it be true with
Yeah.
any theta and theta prime as the first input? This seems slightly weaker than
Huh?
like any theta and theta prime should be indistinguishable, right?
Oh, those are equivalent, right? Because you can say theta is indistinguishable from 0, theta prime is indistinguishable from 0, so theta and theta prime are
But it
indistinguishable.
could be that
No?
theta and theta prime are theta equals theta prime, let's say.
Uh-huh.
As in,
Then obviously they're indistinguishable because
right, no, or to say something along the lines of there could be some hint about whether it's theta or theta prime, but like probability of getting 0 is completely random. Oh wait, no, I think I see it.
yeah, you're saying that, the whole point is that, if you want to distinguish theta from, say, theta prime, if you had an algorithm which could distinguish these two, right, I suppose, yes, I want to argue that if theta is indistinguishable from 0, then, I was just thinking of it like a triangle inequality sort of thing, but maybe there's like a nicer, but probably that's not the right way to, maybe you do need a reduction. Okay, so let's see. So if I cannot distinguish, so if you have an algorithm that distinguishes theta and theta prime, I want to know if I can construct an algorithm that distinguishes theta and 0. Okay.
But the above statement will be true for all theta and theta prime, right?
If you substitute theta prime is 0
If we have
to prove that.
No, you're doing it the other way. Oh no, is it?
So if you can distinguish theta and theta prime for all theta and theta prime, then you can distinguish theta and 0 as well.
yeah.
Then it's a special case. I was just trying to see if maybe that's all we need, right? No, I wanted to say, no, suppose there existed some theta and theta prime for which you could distinguish it.
Then it's not clear that you can distinguish theta and 0. But
Yeah, there should exist some theta which I should be able to distinguish from 0.
yeah.
I can look. It's probably something straightforward. It's just we can look at it. We can look at it later. Yeah. because yeah.
You need to find the case in which you cannot distinguish between theta and 0, but you can between theta and theta. Is it
Yeah, I want to make a reduction. I want to say that if you had an algorithm that could distinguish theta from theta prime for theta, neither of them being 0, then I should also be able to distinguish the encryption of 0 from.
There may be some reduction.
Yeah, but I thought it would be straightforward. Now I can't think of it from at the top of my head. Okay, well that's coming to a homework assignment near you very soon. Good. So yeah, let me write it down somewhere. Okay, good. So, any more homework assignments that people want to add? No. Is everything clear? Okay. Yeah, I'll look into it. That's a good point. I should know this. I'll find out and tell you. Okay, good. So this was the thing. I didn't complete the statement. Okay, so the statement is the following. Then, so you have this part. Then it holds that. So this is the proof. Sorry, this is the statement of the theorem, which is that whether you take z tilde with b equal to 0 or b equal to 1, it will produce the same. Okay, this is negligible. Yeah, I think you could do the reduction. So I think the way it would work is yeah. Okay. Let's do it later because I still have to check the argument if it's fully correct, but it should work. Okay. So this is negligible, and okay. So there are some remarks about x and theta being not just bits but log in lambda size bits, but that's okay. We don't need to worry too much. Okay, good. So now we're going to start with the proof. Nice. Okay, so what we're going to do is we're going to start with a sequence of hybrids, right? So this we sort of discussed in one of the proof sketches. So we consider a sequence of hybrids. As follows. Okay, so we're going to look at, so we'll define hybrid 0 to be the same as what we want to prove, right? So this is going to be the same as z tilde a lambda given b. Okay, also lambda. So this distribution, hybrid 1 of B is going to be the following. Okay, I'll need more space, I'll write it on that side. Okay. Here's the challenger, here's a lambda. So the challenger is going to do the following. It's going to prepare lambda EPR pairs. This we saw, right, last time. I'm just doing it a bit more formally now. On registers C1 A1 all the way to C lambda A lambda. And let C be C1 to C lambda, A be A1 to A lambda. Okay. Theta you get from 0, 1 to the lambda, B prime you get from 0, 1, and x is 0, 1 to the lambda. Be the result of measuring C in basis theta. Okay, and then you send z lambda of theta B prime and A to the challenger or the adversary. The adversary sends you x prime A prime. Okay. Now if B prime equals B XOR I, such that theta I is 0, xi, okay. So if xi equals xi prime, yeah, so this is the usual predicate we check. Okay, so you check whether the B prime you got here matches the thing you were actually supposed to encrypt, right, in the original game, which is here. Because you were supposed to encrypt this thing, right? You were supposed to send this. Now what you did is you used an EPR pair, you made some measurements, and so you're checking if the B prime that you got, which you sent here, right, has the form that you wanted in the beginning. If that's the case, you check this predicate. So you know, I'll just say run this. Let's call this 1. So you do what 1 does. So I'll just set that to 1. Else your output pop. Okay, which is like same as hybrid 0. Okay, so that's the first hybrid. Okay, and then hybrid 2 is the following. So hybrid 2 we are going to this was, yeah, let me write it down properly. This is hybrid this is hybrid 1. Okay, hybrid 1 of B is this. So I'm going to define hybrid X. Sorry. So then we define hybrid 2 of B. And hybrid 2 of B is what? So now what we're going to do is we are going to replace theta with 0 to the n. Okay, and now that we've done this, we'll push this measurement until after we receive the response from the adversary. Okay, let's put it after receiving x prime a prime. Okay, so those are the two changes in hybrid 2. Okay, and we already motivated this, right? Like you can purify it and you can all this. Okay. Huh?
What will the changes be?
Oh yeah, so we replace, instead of sending theta,
Right.
we send 0 to the n. And here, since we don't have to send theta anymore,
We don't have to sample.
yeah, so we sample it after we receive x prime and a prime. And the motivation is this allows us to argue that the theta is essentially independent and these kinds of things, because theta was not even determined, so there's no way the adversary could have dependence on theta, these kinds of things. Yeah.
But why do we even have to sample theta? Oh, to calculate B prime?
Yeah, so theta was used to determine the basis,
Okay.
right? So remember in the earlier what we were doing was, so where's hybrid 0? So hybrid 0, right? So there was x and theta. So you were sending BB84 states. So BB84 states are 0, 1, plus, minus. Now what you're doing is you have EPR pairs, and you're choosing to measure your half of the EPR in standard or Hadamard.
Okay.
So that choice is this theta. Okay. Okay, so that's the adversary. Okay. Okay, and let's introduce a little bit more notation. Maybe I'll do it here. Okay, yeah, so maybe we can just call this hybrid 0 if you want. Okay.
Question. If you're sampling theta after receiving whatever you get from A, right,
Mhm.
the adversary,
Mhm.
then measurement of C in basis theta, will that be replaced with 0?
Measurement of C is not going to be replaced. No, no.
Theta, right?
That is still C, yeah. So you can, yeah, so I don't think we need to have, yeah, so we only need to basically sample B prime, right? To send the message. Is that correct, right? Because you have B prime and then you have register.
For X.
Yeah, so X and theta, so you can sample theta and measure X after you've received this message. Yeah, yeah. It's a good point. Yeah, yeah. Okay. So now what we want to do is we want to, yeah, these are some definitions which will be helpful, right? So we write the, so we define advantage for a given hybrid. So the advantage for the ith hybrid is just the trace distance between hybrid I of 0 from hybrid I of 1 . Yeah. Okay, so the first note is TD is just the trace distance, right? And remember, these things are just outputs of distributions of, they're just density matrices, sequence of density matrices parameterized by lambda. Okay. Okay. So the first note is that advantage of hybrid 1 is at least half the advantage of hybrid 0. Because of the fact that with probability half you would be, because B prime is essentially random, so with probability half you would be identical to hybrid 0, and with probability half you have an output which is the same whether B is 0 or 1, right? So you're going to get, so in the case that they are essentially the same, you cannot distinguish, but the case in which they are different, you can distinguish with at least as much probability as hybrid 0 can be distinguished. So you have at least half probability. Okay, so that's note 1. Note 2 is that advantage.
Could you argue again?
Huh?
Could you argue again why this is second?
Yeah. So suppose you have a distinguisher for hybrid 0, right? So what you can do is, these two cases arise with equal probability, right? Because B prime is random. So whatever B you give me, this B prime is going to be random because B prime was sampled randomly, independent of everything, correct? So with probability half, I'll be in case 1, which is the same as hybrid 0, right? I mean, the predicate is the same, the rest is also the same because you're just purifying the BB84 states. So instead of doing the BB84 states directly, you're purifying it and measuring the 1/2 of the Bell state. Okay, so you're identical to the, so as far as the adversary is concerned, he sees exactly what he would see if he were interacting as an adversary in hybrid 0. Okay. So therefore, if you have a distinguisher that works for hybrid 0, so you would be able to do at least as well with probability half multiplied. So that would be the case. Okay. The next thing is advantage with hybrid 2 is the same as advantage with hybrid 1. So I think, yeah, it's not been fully argued, but you can use the security, right, of the semantic security of Z lambda on the first input, right? So it doesn't matter whether you give it theta or 0 to the n, right? Semantic security said that there's no algorithm that would be able to distinguish, correct? So if you invoke the semantic security, then you can replace theta with 0 to the n, nothing will change. Okay, and you can rearrange these things because they are independent. Once you're in the 0 to the n, it doesn't matter whether you measure them before or after, as far as the adversary is concerned. They'll see the same thing. Okay.
But what do you mean by invoking the security? Because you want to prove
That was in the assumption. It was yeah. So I was assuming that in the hypothesis, I was assuming that you have intuitively, okay, if you want to think about it, I was assuming you have some kind of encryption scheme, and I want to add the deletion property. So I'm assuming you know how to build the encryption.
so Z lambda is secure.
Yeah, so in that sense, I'm saying your encryption scheme is secure. So whether I give you encryption of theta or 0 to the n, you cannot distinguish. That's all I was saying. Okay. And so then the goal for us would be the following. So the goal, which we'll look at next time because we're out of time now, would be showing that the advantage of hybrid 2 is advantage of hybrid 2 is negligible. So that is what we'll try to prove next time. I think I messed up a little bit. I think one of the things requires a bit more proof. Okay, I'll clarify. Okay, I think I missed one of the hybrids. I think in the argument, because one of the steps is actually non-trivial that I just said. So I'll check this and tell you. Okay. So that will be all, and the claim I'll give you the reference and I'll put it in the assignment to complete that one claim that we had in the proof today. Okay.
So assignments are already there in.
It's on the website. Yeah, you can see.
Okay.
Yeah, well, the ones now are useless because they're just about quantum. There's nothing relevant. Okay. Okay. So thank you.